So let's consider the following system. I want to get at, again, a freedom we have in describing systems. How much detail there is in the system gives us more ways to write these fundamental principles and gives us more insight into what's going on. Again, this is something that we bring to the problems. Whatever's going to happen in nature is going to happen. But what happens cannot be affected by our choices of describing the system. What can happen is we'll get some insight into the system, and that's what this point versus complex system discussion is about. So here's a situation. I've got a rod, so it's got a length, so it's got a radius r, so it's got a length 2r. There's two masses stuck on either end of it, m and m, and I'm going to put a force F on each one of these masses. And those forces are always going to be perpendicular to the stick. So force is perpendicular to the stick, but I'm always going to be moving it forward. So I grab each of these masses and I twist them around the circle through one complete revolution. And then I let go. So the thing starts at rest. The final state looks like, let me just draw it like so. I got some velocity here, I got some velocity there. So it's spinning around like that. R, R. It starts at rest, now it's spinning around. So, what does this system look like from the point of view of the center of mass? So, that's the first question. If I'm going to ask a question about the momentum of the system, the momentum always probes what's going on with the point system. So every system, even though it's got things that make it up, it's the total momentum of the system is you add all the momenta together as vectors. There's no structure to a system from the point of view of the momentum. You just add all the momentum together. So in this final state, I've got mv for this first object, but I've got m, we call that minus v, minus mv. P total is equal to 0, even though the individual momenta of this object and this object are not 0. The total momentum of the system is equal to 0, and so for the point particle system, where you cannot see any of the details, you see just the center of mass, so m total times v center of mass squared over 2, that is the kinetic energy of the simple point system, which in this case is 0. At every time I've got a force in one direction, F, I've got a force backwards, F, the net force from the surroundings is equal to 0. Net force is equal to 0. I've got one up, one down. They add to 0, so there is no momentum added to the system, and the center of mass doesn't move anymore. No kinetic energy in the center of mass. And yet, there is kinetic energy in the system. Each one of these objects, I can tell you how much work I do. The work I do, well, in this first object, I take it 2 pi r around the circle. So I have F times 2 pi r is the work I do on the first mass, and there's also the work I do on the second mass, F times 2 pi r. So I definitely do work on these masses, and it winds up in the delta kinetic energy of the two objects. So that's 1/2 mv squared for the first object, plus 1/2 mv squared for the second object. In other words, I know exactly, because of the work I did, how much kinetic energy the object has got. F times 2 pi r is equal to 1/2 mv squared. The center mass of the system tells you what happens if all the mass of the system is concentrated at a dot, and in this case, if all the mass of the system is concentrated in a dot, it's not moving anywhere. No kinetic energy. If I look at the details of the system, the extended system, I can see two pieces of matter, and those two pieces of matter carry kinetic energy. So I did work on them. This is work that you can't see. If I put this whole thing in a black box, so you can't see the spin state, you just know that there's something in there, you know its center of mass isn't moving, you would have to say that its k is equal to 0. This is the same thing as an internal energy. It's just like the thermal energy. You can't see, but it's there. You do work on the object, and it winds up getting that thermal energy. We'll use this distinction between looking at pieces of the system or collapsing it all together to really get an eye at many really hard to understand, really hard to analyze systems.